Hi, welcome back. In this lesson, we're going to dive into theory a little bit and find out how modern renderers work. Renderers such as Mantra's PBR engine, Arnold V-Ray, and so on are all variations of something called a path tracer. In order to explain how one of these works, I've implemented a path tracer in an attribute wrangle node. And there it is. So let's take a look at this setup. Firstly, in this green netbox, I built a very simple camera. It's essentially a grid, and I'll show it here. And we have some controls over resolution. We can scale the resolution. And if I turn off flatwire shaded, and set this to 0.01, we'll be able to zoom in and look at it. So at full resolution, it's quite a lot of points. But we're going to set this to 0.5. That just divides the resolution down so that it's not crazy to work with. Then the next thing we have is an offset point, which is right here. And that will be the camera origin. So there's not too much to it. Next, in the yellow netbox is the scene I want to render. In this case, it's a collection of smoothed star-shaped RBD objects, falling and piling up on a grid with the checkerboard pattern. Note that these don't have any shaders applied. All the color is coming from the CD primitive attribute. Although this is a sim, I'm freezing a frame at the end of the timeline for simplicity. As you'll see, there's enough going on here without needing to have animation as part of it. As you can see, I have 3 wires going into my path tracer wrangle node. We've got the camera film back, we've got the camera origin, and we have our frozen scene. And on the wrangle node itself, we have 3 parameters. We've got bounces, samples, and draw points. I'll discuss what these do shortly. Let's see what our renderer does when it's set to its defaults. If I set the scene to be a template and display the film back, which I can do down here, give it a second, we can see a pretty rough looking render of objects in the scene. This is a direct lighting render of the scene. And by that I mean that only surfaces which have a direct line of sight to a light source are illuminated. The render happens to have 2 light sources built into it. There's a sunlight and there's a blue sky dome. And you can see these here. The sunlight's obviously coming down from this direction, and the sky dome is all around the objects. How is the renderer producing this image? It's ray tracing. It's firing an imaginary ray of light into the scene from every single pixel on this film back, which we're obviously representing as a grid of points. It's finding out what that ray hits, and then it's returning information about that hit point. We can see this in action by enabling the draw points checkbox on the render node. So if I hit that, then we will get some points scattered in our scene. And I'm actually just going to disable that. So now we can see points that have been dropped every time a ray hits something. So we get this really kind of like cool sort of shattered up representation of our scene. But if we look through it from the same point of view as our camera, everything lines up. And then we can go down here and we can, oops, excuse me. We can turn on a subset of the lines between these points. So what we're doing here is we're just creating a line between some of these pixels and some of the corresponding hit points in our scene, just so that you can see these rays going from one place to another. These lines are our primary or direct rays. You'll also notice that we're not seeing any of the rays that hit the sky. I can enable those. And what I'm doing here is anything that doesn't hit an object in our scene, it travels 1,000 units and then it returns a bluish color. It's darker at the top and it's lighter at the bottom, kind of like a realistic looking sky. And I'll just switch that back off. As I mentioned earlier, some areas of the objects are being illuminated. So let's look at how lighting's working. So each time one of these primary rays hits a surface, another ray is fired from that point towards a random point on our sun light source. So I'm just going to visualize our sun rays, and you'll be able to see that. So we have this circular patch up here, which is where the sun is. And the blue dome is where the sky is. But look at the sun for now. If we look closely at where one of these primary rays hits a surface, for example, down here where it hits the checkerboard floor, the primary ray hits there and we cast a sun ray, or it's actually called a shadow ray, towards each light source. If there's another surface in the way and the ray doesn't reach our light source, then that part of the surface doesn't receive any lighting from that light source. And then we're doing the same thing, but for the sky, so I'll visualize that as well. And then if I zoom out, we'll see that we're getting rays cast, this time randomly, or apparently randomly because they're being fired at random points on the sky hemisphere. And if we zoom right out, we'll see that. And that allows us to fill in all the shadows kind of underneath things. So then zooming back in, if a particular surface does have a direct line of sight to a light source, the intensity of the light source is scaled by the angle of the surface to the light source, and that's what gives us this nice smooth shading around the surfaces of objects. So far we have pretty plausible but admittedly fairly noisy direct lighting. This is a little bit like how renderers used to work. If you wanted a surface to be lit, you had to point a light source at it. As you can see, we've got some very dark areas. In fact, some areas like underneath the points of these stars are completely black. In the old days, lighting was very hard work because somebody had to go in and put little point lights into places like this where they had to use an overall ambient light to stop things from getting too dark. It'd be great if we could just have light bounce around the scene and fill in those dark shadows for us. Well, this is known as indirect lighting, and this is what path tracing gives us. We can enable that in our renderer, in our toy renderer, I should say, by increasing the bounces parameter above 1. So if I go up here and I increase that to say 3 and let it cook for a second. We see that our renderer is still very noisy, but we don't have any pure black shadows anymore. We're also starting to see some reflections on the floor. You can see here that we're getting a little bit of reflection from here, and there's some yellow there. It's a little bit hard to see amongst the noise, but it's definitely there. We'll also see that if we look at our cloud of hit points, we're starting to get hit points on objects that are outside the camera frustum, which is to be expected because these are now being taken into consideration as part of our lighting calculations. So let's see what the ray lines are doing now. So now I'm going to disable the primary rays, and I'm going to enable the primary and the secondary rays. And again, we're still culling most of the rays, but we're starting to see that rays are bouncing to different parts of the scene. So what's happening now is that each time a ray hits a surface, in addition to firing a ray to each of the light sources, we're also getting an indirect or secondary ray fired into the scene. This ray is fired at an angle determined by a BSDF, or a bidirectional scattering distribution function. The BSDF models the behavior of a surface by randomly reflecting rays at different angles. For example, if a ray hits the very shallow angle, it might be reflected back at the same direction, but on the other side of the normal. If it hits at a steeper angle, it might get reflected in a random direction. And whichever direction it goes, this secondary ray will then behave exactly like the primary ray, and it can bounce and bounce again until we reach the specified number of bounces. Let's turn this up to a higher number, like, say, 8. And it'll take a little bit longer to cook because it's doing more work. And some of these light rays are now have quite complex paths. If you look at this one, for example, it's traveling down here, it's bouncing up there, then up there. And this means that we start getting some like really nice subtle effects in our render. Each time the ray hits another surface, color information about that surface is accumulated and returned to the original pixel in the film back. With each bounce, more shadow rays are fired, and I'll display those as well. So let's turn on the sun rays. And we see that even at the last bounce, we're getting shadow rays fired towards the sun. So for example, this point in the ground, which is well outside where the camera can directly see, is now being illuminated by the sun. And if I turn on the sky shadow rays, we'll see the same thing. All this firing of rays starts to get quite expensive, as you can imagine. Okay, I'm going to turn off our shadow rays. And we'll zoom back in on our scene. As I noted, we still have a very noisy render. And it's time to do something about that. So the theory behind this type of rendering is that if we fire enough rays in randomized directions and we average the accumulated colors, we should end up converging on the desired or correct values. This is called a Monte Carlo simulation. And it's called that because it's effectively a game of chance. So far, we've only been firing one ray for each pixel, and that's why we have a very noisy image. We can fix that by firing more primary rays into the scene, and we can do that by increasing our pixel samples. So I'll take bounces back down to 3, because that's a little bit quicker. And as soon as that's cooked, I'm going to turn samples up to 3. And this will be a little bit slower to cook. So as you can see, this is now a lot less noisy. There's still plenty of noise there, but it's not too bad at all. For each point, we're now seeing 3 rays in the X direction around each of the original points, and 3 rays in the Y direction. And we end up with 9 rays in total. And those are being fired from points with random offsets from the original pixel. So each of those 9 rays per pixel, and we'll take a look at the rays here. As you can see, we've got a cluster of rays for each of them. So each of those 9 rays is bouncing around the scene off other objects, and all the shadow rays are being fired off, and all those bounces are still happening, and it's all being returned back to the original source point or source pixel, where all the rays are averaged together to produce the final color. And if we increase the number of samples again, it'll get cleaner still, and obviously at the expense of longer render times. I'm going to kick off one with 12, but I'm going to disable the draw points because that's going to start consuming way too much RAM. Okay, let's set the samples to 12, which should give us 144 samples per pixel. Okay, and it completed. I think it was around 2.5 minutes. And that's not bad. Again, there's still some noise, but you know, a couple of minutes a frame for a reasonably smooth image at half resolution isn't bad for something thrown together in a wrangle node. It's also worth saying that this implementation is very much a brute force one, and it's obviously lacking a lot of the bells and whistles that you'd see in a production renderer. One particularly important difference between this and something like Mantra is that Mantra has much more fine-grained control over things like sampling. For example, Mantra will let you increase the number of secondary rays as a multiplier on top of the number of primary rays. So for each of our primary rays, we can fire more than one secondary ray. A very sort of simple path tracer like this one doesn't really do that. So that means that you can fine-tune the rendering engine to clean up noise in particular areas of your scene. For example, you can have more rays used for reflections and more rays used for refractions and so on. Right now, if we want to get rid of noise in the reflections, we just have to crank up the samples overall. In this lesson, we've looked at the way that a path tracing renderer fires primary rays into the scene, and that these then spawn secondary rays and shadow rays. We also examined how firing multiple rays can be used to anti-alias our renders. I hope this insight into how renders like Mantra work will help you to produce efficient and beautiful renders in the future. I'll see you in the next lesson.